Good afternoon. My name is Jesse Heilman from here at Carleton University, obviously, and I am the regional coordinator for this leg of the 2024 CAP lecture tour. Before we get started, I have a couple of announcements about how the talk will proceed. All questions are going to be handled at the conclusion of today's presentation, and we'll alternate between questions from people attending here in person and people participating virtually. For those attending virtually, please post your questions in the virtual chat at any time. Your questions will be posed anonymously to the speaker by the MC. And for those attending in person, please wait until you are called upon to ask questions and then use the microphone, which I guess we just have a room mic here. We don't have an actual mic so to ensure that the virtual participants can hear it. All students participating today, both those online and in person, are encouraged to remain after the talk and participate in a 15 to 20-minute informal discussion with the speaker. And we also invite faculty and other attendees to participate as well. So now it gives me great pleasure to introduce our host for today's CAP lecture, Professor Daniel Solarski, who is a professor of physics here at Carleton University, and he will introduce our speaker.
Thank you, Jesse. Yeah, I'm going to introduce the speaker. I'm also going to introduce the CAP lecture series for those of you who aren't familiar. So first, let me begin by acknowledging that the Carleton campus is on the traditional unceded territory of the Algonquin people. The Algonquin people have lived on this land since time immemorial. We also acknowledge that North American settlers have treated the First Nations, Inuit, and Métis of this continent unfairly and unjustly, and we have a lot of work to do to progress towards reconciliation. So CAP, the Canadian Association of Physicists, is putting this on. And what is CAP? CAP is a national network of 1,700 member physicists working in Canadian educational, industrial, and research settings. CAP operates as the voice of Canadian physicists to government, granting agencies, and international societies. And we sponsor, or they sponsor and support physics events and activities in Canada, including the CAP Annual Congress, which is coming up this year in May at University of Western Ontario, the National Student Physics Conferences, the publication of Physics in Canada, and of course the CAP lecture tour. And CAP provides programs for students. So for example, professional certification, undergraduate student conferences, graduate student conferences, prizes, scholarships. The CAP Congress is great for students to attend, especially if you have research to present. And there's also a student advisory council. So please join the Canadian Association of Physicists. It's free for undergraduates during the BSc and free for graduate students during their first year. So go to cap.ca/membership to join. All right, so I would like to introduce Professor Mohlabeng, who will be talking about searching for dark matter from the laboratory to the cosmos. Professor Mohlabeng focuses on his research on physics beyond the standard model and dark matter in particular. And he's currently a professor at Simon Fraser University. So welcome, Professor Mohlabeng.
Thank you very much. First of all, to all of you, I heard that my talk was nominated by the undergrads here. So thank you for choosing my talk. And I want to thank CAP for bringing me here and also my host for hosting me. So today, usually before I give my talks, I like to say a little bit about my name. So as you can hear, I have an accent, and I am originally from South Africa. And in my home language, which is North Sotho, my name means remember. Now I've been living in North America for more than 10 years. And two things have happened with regards to my name. People have not remembered my name because it's too long. And people can't pronounce my name. It's pronounced Gopolang, with a H at the back. So this is why you would hear some of my colleagues calling me Gopi, or half of it is, half of Gopolang is Gopi or Gopi. So I'm going to tell you today about searching for dark matter from the laboratory to the cosmos. And I'm going to keep this talk quite light. So it's going to be a bit of storytelling in there, so please don't fall asleep. So when we look at pictures like this, and I look at pictures like this of galaxies and stars and gas and stuff, it reminds me of when I was a kid going to the village, away from the city where there was no light pollution. And I'd look up in the night sky and I'd see this beautiful picture of the Milky Way, and I'd see stars, galaxies, gas, and all this stuff and all that stuff. And I remember thinking to myself, this must be all there is in our universe. You know, there's so many stars, so many galaxies out there. That must be it. And as I grew up and I learned more about astrophysics, I learned that actually all that stuff that we see from gases, galaxies, stars, they actually only make up about 5% of our universe. And the rest of the stuff that our universe is made of is actually dark. So 95% of our universe is quite dark. Now, this I couldn't help myself, so I had to use get a reference of Star Wars in here. So allow me to take us to the dark side, and let's learn a little bit more about this our dark universe. So a very large component of our universe, as I mentioned, is dark. About 26% of this is made up of an entity we refer to as dark matter. All we know about dark matter is that it exists and it has some gravitational interactions with the rest of the star model. Then there is another component, an even less known component, which we simply refer to as dark energy. We know almost nothing about dark energy. So as mentioned before, my work is on dark matter. I do dark matter research, so I focus mostly on this blue region. But if you have any questions about dark energy, if I can answer them at the end, I will try. If not, then I will direct you to people who I think can answer your questions. I want to talk about the evidence of dark matter. And some of you may have seen this similar, different iteration of this type of talk. Some of you will not have seen this talk before, but nonetheless, it's always good to repeat things and we learn them better. So before I talk about the evidence of dark matter, let's go back to, before I go to out in the universe, let's stay home for a second. Let's look at the solar system. So we know that in our solar system, I have the sun, and the sun is massive and causes a big gravitational field that traps planets and makes them orbit around it, right? And in the sun, this whole system can be explained by Newton's laws of gravity. So we know that this big gravitational pull is the force that is causing these planets to stick to the sun is Newton's laws of gravity, and the force that is causing the planets to rotate around the sun is the centripetal force. Now, Newton's laws of gravity also tell me something else. That's something quite important. So Newton's laws of gravity tell me that planets that rotate closer to the sun, planets that are this distance closer to the sun rotate much faster, and planets that are further away from the sun rotate much slower. And using this information, as we know what the rate at which the planets are rotating around the sun, we can measure the mass of the entire, or we can calculate the mass of the entire solar system, and this gives us something about 2 × 10⁻30 kilograms. And from this, we can infer the mass of the sun to be about 1.9 × 10⁻30 kilograms. Okay. Now, let's do something a little bit crazy. Let's imagine that the sun is there, but it's invisible. And so perpetually, if I look at it in the earth, we'd be actually living in perpetual darkness. There'd be, how many of you have seen the movie, I think 26 Days of Night or something like this? It's a zombie movie. Okay. Yeah. So imagine that we were living in like this, except there would be no zombies. We would just be living our normal lives, but there'd be sun. We would be getting heat from this object, but we just would not be able to see it. So we can use Newton's laws of motion again to look at how the planets rotate around this object that we cannot see, and find that the entire mass of the solar system is still 2 × 10⁻30 kilograms, and that the mass of this object that we do not see is about 1.9 × 10⁻30 kilograms. So even though we don't see it, we can still use our knowledge of dynamics and mechanics to calculate the mass of objects. And this is really how the idea of the gravitational evidence of dark matter. Now let's try this again. Okay. So dark matter was first, the idea of early evidence of dark matter was first reported by Lord Kelvin in 1884, who looked at how stars were moving around the Milky Way galaxy, and he was able to use this to estimate the amount of dark matter or the amount of unseen matter that is around our Milky Way. And the term dark matter was first coined by Henry Poincaré in 1906, who used the results from Lord Kelvin's work to give a public lecture. Now, so since then, the idea of there is some matter that exists that we don't see has been what was around. And then a few years later, Fritz Zwicky, who used the virial theorem. So Fritz Zwicky, who used the virial theorem, was able to calculate looking at a larger cluster, a larger system of galaxies, known as the cluster of galaxies, which is called the Coma cluster of galaxy. Using that virial theorem, he was able to calculate, and just by looking at how galaxies were moving in this cluster of galaxies, he was able to calculate that there was 400 times more mass than he could observe in a telescope. So he labeled this dark material. And naturally, as we are all skeptics, no one believed him until in the 70s. Vera Rubin was able to, Vera Rubin and the collaborators were able to use some technology, or what was at the time very sophisticated technology, to calculate the most precise, to make the most precise measurements at the time of stars that were moving around galaxies. So they looked at if I look at a galaxy, if I pick one star and look at its motion around the center of the galaxy, how well can I measure that as a function of the radius? So they looked at these galaxies, and they were able to measure the stars, the rotational velocities of stars. And what they found is that as I move from the center of the galaxy to the outer parts, the rotational velocity increases and stays the same. Now, this is against intuition, because Newton's laws of gravity tell us, again, from what we saw in the example of the solar system, that if I have an object rotating around a more massive object, I can use this balance of forces between the centripetal force and the gravitational force. Then I can calculate the rotational velocity that goes as gm over r. And what we expect is that as I go from the center of the galaxy, I increase because the mass term increases. It goes down when the mass starts going away, and this goes down as a square root of 1 over r, or 1 over square root of r. But this is actually what we actually measure is the following. Now, looking at it face on, it seems this is actually what I have to do this again. So if I look at this face on, so this tells me that this is on the right picture, on the left-hand side. This is what we actually observe. So galaxies have dark matter, and this is how a galaxy that has no dark matter would be moving. So if a galaxy had no dark matter, that means that it would be rotating the center much faster than it would be at the outer edges of the galaxy. But what we actually observe is that the galaxy is rotating almost at the same rate at the outer edges as it is at the center of the galaxy. So this is one evidence that there must be some material or some matter that we don't see that is out at the edges. And again, using Newton's laws or our knowledge of dynamics and mechanics, we can calculate the amount of, we can infer the mass of the entire galaxy and the mass of the, that there is some certain ratio of dark mass to normal mass in a particular galaxy. Now, let me throw a spanner in the works. What if Newton's laws are wrong? Or what if our understanding of Newton's laws in a galaxy are not correct? And this idea is what we call modification of Newtonian dynamics, which says, forget dark matter. I don't need some new particle or some new material that tells me that there's something new out there. What I can do is just modify Newton's laws. I can add its mathematics. I can add just the constant to Newton's laws, and lo and behold, I can actually fit the data much better than any dark matter model would be able to. And I'm bringing this up because, you know, we are theorists. I'm a theorist, so we deal with theory and we try to match data. And so any theory that comes to me and says, well, I can match the data, if it's plausible, then I have to think about it. What I'm going to show you actually is that modification of Newtonian dynamics only works at one scale, whereas dark matter is actually consistent towards all the scales in our universe. So let's move on to larger scales. So we were talking about the scales of galaxies. So I started the story with the solar system. I moved on to galaxies. Now I'm going to move to groups of galaxies or clusters of galaxies. So when I move to these scales, now I have to throw away Newton's laws of dynamics and start looking at general relativity. And one application of general relativity is gravitational lensing. And so gravitational lensing tells me that if I have a massive object sitting out in space somewhere, it bends space and time. And when it bends space and time, any light that is coming nearby that object is going to be bent around that object. And so if I have a galaxy at the background, and I have this massive galaxy cluster, the light around this that passes through this galaxy cluster is going to be bent. And so we call this a gravitational lens, and this is the lensed object. And so I can see this lensing effect in my telescope. And so this lensing effect just looks like something like this, where I have these rings or distorted image of the galaxy in the background. And so even though I don't necessarily see the galaxy cluster in my telescope, if I see this kind of image, then I know that there must be some background object that is being lensed by this big galaxy cluster. Now, again, let's do this thought experiment. Imagine that the galaxy cluster is there, but it's not. I just don't see it. Okay. So again, I'm going to do the same thing where I still see this lensing effect from the background galaxy, but I just don't see what is lensing that object. And so this is another piece of evidence that we have that dark matter exists at those scales. Now, one of the biggest experimental or biggest pieces of evidence that we have that dark matter exists is from the bullet cluster of galaxies. So if I look at this this animation over here, it shows me two galaxy clusters that went through each other, kind of merged, and the blobs, the blue blobs around them, is the dark matter halo. I'll play it again, and the red is the visible matter. So as these two are interacting, I see that the dark matter, or what is a representation of the dark matter, does not interact very much, but the gas and the stars in those clusters actually interact. And what we see, actually in our telescopes, we can actually see this gases, or the red stuff. But what we don't see is the blue stuff. And how we know that the blue stuff is there is actually by looking at this lensed image. So everything at the background stars and galaxies, actually lensed by these blobs of dark matter over there. And interestingly, one of the pieces of evidence that we have that dark matter has some sort of self-interaction, and we can place limits on the scattering that it has with itself, is from the bullet cluster, by the fact that these two particles or these two blobs were able to go through each other without interacting or distorting very much. So, unfortunately, I cannot modify gravity at these cluster scales and still be consistent with the modification of gravity at galaxy scales in order to explain the data. So if I had to modify general relativity at that scales, I would have to come up with a completely new theory that is inconsistent with how I modified gravity with Newton's laws. And so if I did modify gravity here, then I would have to have modification of Newtonian dynamics, plus another completely different theory, which is in there are many theories that try to do this, like FR gravity or many other theories. However, with dark matter, I can explain dark matter at the clusters, galaxy scales. I can explain dark matter at the cluster scales. And what I'm not going to show you here, where you just have to take my word for it, I can also explain dark matter at the CMB scales and small scales in the universe. Okay. And so this is what one thing that shows us that dark matter must exist, or the gravitational evidence that we have that dark matter must exist, and any other modification of Newton's laws or gravity that is going to be there can happen, but it's not going to happen consistently enough for anyone to believe it. All right, so I've shown you only two pieces of evidence. I would love to show you the rest, and I'm sure some of you have seen the rest. Unfortunately, I have only 45 minutes to talk about the rest of dark matter. So I'm going to show you here, and you can ask me about the rest if you're interested later. Now, why does dark matter matter? Why do I study dark matter? Why am I here kind of preaching to you about the fact that dark matter exists? I'll tell you why I'm interested in dark matter. And to tell you this, let's do a thought experiment. So my claim is that I would not be here, you would not be here if dark matter did not exist. Okay. And my claim for this is that if I did a thought experiment, let's take a rubber sheet, stretch it out. This rubber sheet, imagine this is a space-time continuum, put a bowling ball in the center and take some millions and millions and many smaller balls like ping pong balls, marbles and stuff, and just throw them there. We all know that they're going to go towards the center because the bowling ball has caused some sort of potential wow in there. Now let's imagine that I start shifting this rubber sheet. Let's just start moving it in a certain direction. And then I make this bowling ball invisible. Okay, I still have these other balls that form some sort of shape around that central object, even though I don't see it. Right? I've now just formed a galaxy. And in my galaxy that I've just made, I have a solar system, I have the sun, and I have some planet that is just at the right distance away from the sun that it creates life. And I'm born, and you're born, and everyone is happy. Right? And so without dark matter forming these, being there to form gravitational potential wells and having baryonic matter or standard matter falling into these gravitational potential wells, forming galaxies, we would not actually have the structures that we have today. And this is one of the properties that we know about dark matter, that it must be moving slow enough at the time of structure formation to form the galaxies that we have today. And I'll talk a little bit about that. Now, an inconvenient truth about dark matter is that we don't know what dark matter is. And this is part of actually why I'm so excited to study dark matter, is that we don't know what it is. So it gives me great pleasure to go on a kind of a treasure hunt. You know, Easter is coming up, so we're going to do some Easter egg hunts. So I'm constantly in my life doing a dark matter hunt. And we don't know what mass it has. We don't know whether it has spin. Does it decay before the age of the universe, or does it decay, later than the age of the universe, i.e. is it stable? We know it interacts gravitationally. Otherwise, I would not be here talking about this. But besides gravity, what other interactions does it have? Is it an elementary particle like an electron? Or is it a bound state of particles like the proton? Or bigger bound state that has many constituents, like, I don't know, whatever bound state you can think of. Now, if it's a particle, it must be a new particle. Why must it be a new particle? Well, you're talking to a particle physicist. I think of everything as particles. But it could be anything else that you can think of, as long as it matches the experimental data that we have today. And the most motivated for this is what we have in particle physics. Now, what does this mean? So let's look back at these this plot, this pi energy distribution. So one of my main questions that I ask myself is, what is the fundamental physics that governs all these different sectors? And as I've mentioned, my most important question is, what is the fundamental physics that governs the dark sector? So before I do that, let's talk about the fundamental physics that governs the visible sector. So the visible sector is governed by the standard model of particle physics. So here I show the standard model as it's separated into matter particles and force carriers. So we know that there are four fundamental forces in nature. There's gravity, electromagnetism, weak force, and the strong force. Electromagnetism is carried by the photon. The weak force is carried by the W and the Z bosons, these two here, and the strong force is carried by the gluon. And unfortunately, in the standard model, there is no gravity. We cannot explain gravity in the standard. Now, I've kind of given you this picture. I'm telling you how everything interacts, but I've given you a picture of a standard model, kind of like a periodic table of elements. So I'm going to burn this picture. It doesn't work.
Yes.
Okay. So it took a while to burn, but it burned. And so I'm showing you a picture. I hope everyone online can see. I'm showing you now a more interactive picture of the standard model. Okay, worth the wait. That's awesome. And so we see a picture. We see a more interactive picture of the standard model of particles physics, where the gluons, the particles that have interacts with particles that have strong charge, because it's the carrier of the strong force. The particles that have electromagnetic charge interact with the photon, and everything that has weak charge interact with the W and the Z bosons. And everything that has mass interacts with the particle called the Higgs boson, which is responsible for giving all these particles their mass. But you may say, well, hold on a minute. These particles called neutrinos actually have mass in the star. We know that they have mass. We've seen experimentally their mass, but actually in the standard model tells us that effectively they don't have mass because they don't interact with the Higgs boson. But so this is where another question of particle physics is, where does the neutrino masses come from? And it seems to indicate a requirement for some new physics that can explain these neutrino masses. And so the standard model is essentially complete because we theorized all these particles and we discovered them. But none of these can actually explain what dark matter is. So then, what exactly is dark matter made of? Well, number one, we simply have no idea. This is why we're looking through this through every lens. However, one thing we do know, or a few things that we do know about dark matter, is that it must be cold. By this, I mean that it must be non-relativistic at the time of structure formation. And so remember that little exercise that we did with that we thought of with stretching a rubber band and making a galaxy. If the dark matter was moving really, really fast during the time of structure formation, the baryons would not be able to get trapped efficiently by the dark matter. And so we would not be able to form efficiently the galaxies that we see. We would still form some galaxies because there's some particles that are moving really fast, but they would be very puffy. And this is not what we see today. So this gives us a constraint that tells us that dark matter must have a certain property. And by the time of structural formation, it must be non-relativistic. It also must be super long-lived, because if dark matter decayed into something else before it formed these structures, then these structures would not have formed. So either it must be really long-lived, i.e. it decays after galaxies are formed, and we would look for these type of signals, or it must be very long-lived such that it actually does not decay in the lifetime of the universe. Also, it must be some state that is not part of the standard model, because if it was part of the standard model, it would interact through three forces: electromagnetism, the strong force, or the weak force, right? It is possible that dark matter may interact with us through the weak force, because the weak force is actually quite feeble, and it is possible that it interacts through that. But it cannot interact through the strong force or the electromagnetic force. Otherwise, we would have seen it a very, very long time. It also may interact not only through the weak force, but through some new force that we haven't seen as yet. And one exciting part about searching for dark matter is also searching for associated new forces that it may come with. It may interact with the standard model through. Okay, so the range of possibilities of what dark matter could be are huge. So you may have heard talking about WIMPs, weakly interacting massive particles that have mass between 1 gigaelectron volt, that's about a proton mass, to about 100,000 gigaelectron volts. So that's about 1,000 times the xenon atom's mass. If I go heavier than that, I go into the ultra heavy regime, where I'm talking about particles that can be as heavy as the Planck scale, up to 10 to the 19 gigaelectron volts, or even heavier than that. In principle, they could actually also be heavier than the sun in the form of primordial black holes, or black holes that were formed early in the universe. If I go lower than WIMPs, I go to masses that are between the electron and the proton in mass. This is what we call the sub-GeV region. If I go lighter than that, I go into the ultralight regime. So some of you may have heard of axions. Axions lie in this region of parameter space. And now these all require different experiments in order for us to see all these dark matter theory particles. And so also the range of theoretical possibilities is also quite huge. And so this is a Venn diagram that was created by Professor Tim Tate at the University of California, Irvine. And he looked at what is the kind of intersection between all these different theories of what dark matter could be. Some of you may have heard of supersymmetry. There's extra dimensions. There's sterile neutrinos, sterile neutrino dark matter, axions, all the different types of dark matter, which follow certain rules that we have set that can give us some sort of clue about where dark matter is. And so far, we haven't seen any of this, but what we have learned is where dark matter is not, and what it kind of gives us a guideline of what dark matter could be and where to search in the future. Now, it is possible that dark matter may be hiding in plain sight. And we must explore different scenarios and ideas to test these dark matter theories. I must say, either you're all very nervous or I'm making you nervous. Usually this gets people to smile. I just got you to smile, that's great. All right. So how do we find dark matter? There are many ways that we can look for dark matter. I say it's 3.5 ways to search for dark matter. So there are 3 ways I can look for dark matter in the sky, at colliders, and at underground detectors. The half comes from what we have observed from cosmology. Cosmological and astrophysical data tells us that there's a certain amount of dark matter that is there in our universe. And this is how we know that the universe contains about 27% of dark matter. And so if you come to me with a theory and say, I have a theory of what dark matter could be, the first thing I'm going to ask you, does it actually match the amount of dark matter that should be observed in our universe today? You go back and you calculate and you say, yeah, it does. Then you come back and then we say, okay, how do we actually look for this dark matter in our universe today? So one of the ways that we can look for this is in the sky through what we call indirect detection. So indirect detection is the idea that in high dark matter dense regions, like in the center of our galaxy, for example, there's a higher probability for 2 dark matter particles to meet each other, annihilate, and convert their energy into standard model particles. And here, what I'm doing is that I'm using just the concept of E equals to mc squared, where I'm converting energy just into mass. So if I have a dark matter of a certain mass, these 2 particles annihilate each other and convert their energy into standard model particles. And I can look for this energy in the form of these standard model particles. So for example, if dark matter annihilates into high energy photons, I can look for gamma rays in the Fermi Gamma Ray Space Telescope. I can also look for neutrinos if the final states of these annihilations are neutrinos, and I can look for these at the IceCube Neutrino Observatory. So one of the things that I can look for is what we call the thermally average annihilation cross-section. So the thermally average annihilation cross-section is this value over here. That just tells me what is the probability of these 2 particles to interact, given the fact that these particles may have the same mass, but they actually have different velocities. And so I'm just going to thermally average those or velocity average them and say, how is it possible? What is the probability of them interacting? Then I have to look at the flux that I can calculate from this and measure that, compare that with the flux that I would get from an experiment like Fermilab. The other thing that is really important is to look at is, the other thing that is really important to look at is this density squared here. So all these experiments are sensitive to the density squared of these interactions. And the reason it's squared is that I have one density for one dark matter particle and another density for another dark matter particle. And what we're showing here is I can convert this, I can kind of do a fitting and look at this as a parameter, as a function of the dark matter mass. And what we see is that experiments that I've actually run are looking in this gray region over here. This is really slow. The experiments that I've run are in this gray region of parameter space over here. And experiments that are coming in the next few years are going to be able to cover a much larger parameter space. And these are much longer term experiments. Now, why is this line important? This line is important because any model of dark matter must match the amount of dark matter that we see in the universe today. And that dark matter may have been produced in thermal equilibrium with the standard model path. So I'm not gonna, this is all I'm going to say about this. You can ask me later. Again, I'm running out of time, so that's all I'm going to say. But this is actually a theoretically motivated parameter space. So as a theorist, we have to work with experimentalists who can tell us exactly how do we find the theories, how do we test the theories that we come up with in our everyday experiments. So another thing that I can look at is collide experiments. So how do I look at, how do we produce dark matter in a collider? So now I'm looking at this arrow going this way. I'm taking the energy of standard model particles and producing dark matter. So if you look at, I hope this works. So if you look at this little simulation over here, I have 2 red dots. I'm producing these red dots. And as I'm producing them, I'm just accelerating them in this really large ring. Now, it turns out that these red dots are actually bunches of protons. So each dot has 10 to the 11 protons in it. And I'm just accelerating them. And as they move around this ring, they move faster and faster and faster and faster. Once they reach maximum speed, I allow them to interact in some thing that I put a lot of sensitive material around that I call a detector. And lo and behold, boom, I have an explosion of these particles that can, so I convert these standard model particles into possibly dark matter particles. And so I can search for this at experiments like Atlas, which is over here. So as you can see, this is the scale of a human. So these are really, really big experiments here. Or I can look for, instead of having a center of mass collision, I can look at a fixed target experiment where I shoot a beam of electrons or protons at some fixed target material. And so I shoot a beam of protons into this fixed target. I can produce the dark matter particles that comes out of this. I put a detector way downstream. And if the dark matter is long-lived enough, it will actually reach my detector and interact inside of the detector. So these are some of the ways that we can search for dark matter or produce dark matter in our laboratories. Another way that I can do this is by just taking advantage of how we are moving in our solar system or how we are moving around our galaxy. So we know that the solar system in our sun, or our solar system is rotating around the galaxy at 220 kilometers per second, right? So as we're moving around this galaxy, imagine that I have a ball of dark matter that is just a gas, a spherical gas of dark matter particles that this galaxy is rotating around. In my frame, I see the dark matter coming towards me at 220 kilometers per second. In the dark matter's frame, it sees me coming towards it at 220 kilometers per second. So all I need to do is just actually sit there, build a really, really large detector, and wait for a dark matter particle to just come in and interact inside that. It's like a really almost lazy way of detecting dark matter. It's not that lazy. So what we have now is that I have this WIMP wind, or this dark matter wind of particles that are hitting me. What I need to do is just build a detector, wait for a dark matter particle to come in, cause a recoil, and I can put some electronics over there as it hits a nucleus or an electron. Photons shoot out from that, and I can record those photons, and I can actually try to kinematically reconstruct this interaction and try to understand what is the kinematics of this dark matter particle, or the properties of that dark matter particle. Now, this process is known as direct detection. Now, we can look at it in various ways. So one way I can look at it is through dark matter nucleon scattering, where dark matter can interact with a proton or a neutron. And I can have a coherent interaction. So a dark matter comes in, hits this neutron or proton coherently, causes it to recoil. And the rate is given by this long equation over here. Now, this unfortunately is cut, but the main thing to pay attention to here is the scattering cross section. So what is the probability that dark matter comes in and interacts with my nucleus in here? And there's also a velocity distribution. The fact that if I was to freeze this ball of gas, the dark matter would actually just be moving, vibrating in various directions within itself. But then now I'm adding my motion into this ball of gas. And so there is some sort of velocity distribution of the dark matter particles. So even if we did detect one dark matter particle, we cannot determine what its velocity is. I'm just sampling from a distribution, a velocity distribution. And so how we usually represent this data is I have a cross section. So that's that sigma chi n as a function of dark matter mass. And what we see here is that actually so this part is what we have searched for from experiments, and all of this, the other parts are experiments that are currently operating, haven't reported the results yet, but some are coming up in the near future. The gray region is actually quite interesting. If I build a detector that's big enough that neutrinos can actually come in, those neutrinos are going to, or that experiment is so sensitive that it's also sensitive to neutrino interactions. So neutrinos that are produced from the sun, from our atmosphere, from distant supernovae are going to come into that detector and give exactly the same signal as a dark matter signal. And at that point, I cannot determine whether I have a neutrino signal in my detector or a dark matter signal in my detector. And so this is where we have to come up with different ideas. And one idea that people have been looking at is the idea of directional detection. Can I actually determine the direction in which the dark matter is coming from inside my detector? And so if I look at this, I see this region over here. I see this region over here that is currently not quite occupied. So maybe new technologies or future experiments will be able to reach that region of parameter space. But so far, we cannot reach that yet. And so naturally, we ask ourselves the question, what happens at lower masses? What can we do over here? Are there opportunities for us to search for dark matter in this region? Okay. And so what lives here, or who lives there? So it turns out that actually nuclear recoil experiments, the reason that that region of space is open is that nuclear recoil experiments are not very sensitive to dark matter masses in this region of parameter space. And the reason for this, a little bit more mathematics, is that the recoil, so if a dark matter comes in, hits a nucleus, it causes it to recoil, I can calculate that energy. That energy of recoil goes as the reduced mass times the velocity squared over the mass of the nucleus. So I can calculate that if I have a 500 MeV dark matter mega electron volt dark matter particle that hits a xenon nucleus, I can calculate this to be about 5 electron volts. Now the thresholds of these experiments, so below, there's a certain energy below which these experiments actually cut out the data because there are a lot of backgrounds, so they cut this out, is about keV. So if I have a dark matter particle coming in at 5 eV, we're not going to see that in the experiment. So think of this as a ping pong ball hitting a bowling ball. Yes, there's going to be a recoil. I'm just not going to notice that recoil. So another way that I can do this, I can maximize energy transfer to the target is by looking at a lower mass target. We all know what an atom looks like. I have a nucleus with electrons orbiting around that nucleus. So instead of hitting a nucleus, I can hit an electron and cause an electron instead to recoil. And there are a lot of searches that have been looking at this as well, where again, what I'm going to look at is the probability of the dark matter scattering with the electron. I have that velocity distribution part again, and I also have an atomic effect. So for those of us who are interested in atomic physics, I actually can apply atomic physics to dark matter studies as well. So I need to understand how does a dark matter particle come in and ionize my nucleus. And different nuclei have different ionization energies. So I need to study those well in advance. So I need to study those quite well. And so I'm running out of time, so I'll speed this up. So that's one way to maximize the energy. So if I have a dark matter that is slow moving, comes in and hits an electron, I can actually look for that. But another way, an alternate way that I can look for dark matter is to look for energy transfer that is much faster, for dark matter that is moving much faster. So before I talked about dark matter moving at 220 kilometers per second, which is about 10 to the minus 3 times the speed of light. Now imagine that I have a much faster moving dark matter. And I'm going to talk about how do we get that. If I have that now, the energy transfer is no longer 5 electron volts, but it's 50 kilo electron volts. And the energy transfer to the electron is quite huge. Now I have mega electron volt energy transfer to this electron. And there are ways that we can search for this dark. Now this actually opens up a lot of opportunities for discovery. But that's when you stop me and say, hold on a second. You're the one who told me that dark matter should not be moving so fast in our galaxy. So if it's moving that fast, how is it that we can actually form structure? And that would be correct. Any dark matter that is very fast moving in our galaxy today has to be a subcomponent of the non-relativistic dark matter. So I have to have formed the galaxy. So there must be some non-relativistic dark matter. And a small fraction of that can be the dark matter. So that's another constraint that I have to work in. So now I have to ask, what are the different ways that I can get accelerated dark matter? How do I accelerate dark matter in a galaxy? So one way that I can do this is to look for cosmic rays. So I think you all understand what cosmic rays are? Yep. So I have some violent phenomenon that happens in the universe somewhere, like a blazar, an AGN, which releases very, very high energetic standard model particles. They travel all the way to the Earth or near the Earth, and they interact with dark matter, just minding its own business. They hit the dark matter particle, cause it to recoil, having a large amount of energy. And this dark matter comes into the detector and deposits a lot of energy. And so what I can look at is now I'm looking at detectors that were not actually accessible to me before, but now they're accessible because I have a lot of energy that I'm depositing inside my detector. So neutrino experiments are now accessible to dark matter detection as well. Whereas before we never thought about that with a non-relativistic particle, because neutrino experiments have very high thresholds. So anything below, let's say, 100 keV or MeV, they throw out. But now I have a dark matter particles that is coming in and just depositing a lot of energy inside this detector, kind of mimicking a neutrino as well. So that's one way that I can search for these, or another direction that I can search for these dark matter particles. Another way that I can look for this is through neutrino acceleration. So I have a solar neutrino. We know that the sun produces a lot of neutrinos. So if I have dark matter that is outside the sun, neutrinos can come out of the sun, hit this dark matter and cause a large boost in the energy, and these neutrinos can come into the earth and interact. So here's a plot where I look at the neutrino flux, and you can see the mass, the velocity of this dark matter coming from interactions with these neutrinos is actually quite much larger than, say, the non-relativistic dark matter particles. So as you can see here, your very own Professor Yue Zhang has written this really wonderful paper. So if you're interested in this, please talk to him more about that. There are other methods of upscattering, which I'm not going to talk about because I've run out of time. Okay, and so what I've worked on a lot is looking at non-minimal models of dark matter. So if I have two dark matter candidates, both are stable in the age of the universe, but one doesn't talk to the standard model, the other one talks to the standard model, and acts kind of like a mediator. And so if I have this heavier dark matter being non-relativistic, it can annihilate into a lighter dark matter, and the lighter dark matter comes out very energetic. It comes in and deposits a lot of energy inside the detector. And the experiments that I can look at are a lot of very, very large volume neutrino detectors that have very large energy thresholds. And one that we're really excited about in Canada that's currently being built in the coast of Canada is called the P1, or the Pacific Ocean Neutrino Experiment. And that's something that we can look at to search for dark matter. And so, in summary, I've tried to show you different, or try to talk about the evidence of the existence of dark matter, kind of from a somewhat maybe different lens, point of view or lens. And we've been searching for dark matter using the traditional methods for a long time. Now, this doesn't mean that because we haven't seen a signal, we should stop, but we have now actually a lot of opportunities with a lot of experiments coming online, a lot of data from cosmology and astrophysics that actually gives us more opportunities and makes it more exciting for us to look for and test our dark matter models and scenarios. So I think right now, for me at least, it's a very exciting time to be thinking about and working on dark matter. Thank you for your attention.
Fantastic. Thank you for the wonderful talk. So as of yet, I don't see any questions online, but if you are listening online, please submit questions and we can take them. But for now, are there any questions in the room?
Yeah, you mentioned that neutrinos don't gain mass through the Higgs boson. There's some other mechanism giving them mass. Do we know how dark matter is getting its mass? Like, do we know whether it's or?
No, we don't. So you can treat dark matter in a similar way as neutrinos. We don't know where its mass comes from, but most theories that predict that this dark matter candidate will give you a mechanism for producing its mass.
Okay, thank you.
I had a question. At the start of your presentation, you gave a couple went for the reasoning of gravitational stuff. There was one, I believe it was the sixth one, talking about no, the methods of like how we know it, like gravitational effects, and there was mass scales of. Really, I don't have the exact. I think it was a bit past this. It was
The evidence for.
the evidence for dark matter. That's what.
Okay. This one?
2 slides back, I believe.
That's back. Oh, this one.
Yes. Yeah.
Okay.
Matter power spectrum.
Yeah.
I'm wondering if you could give a quick overview of what that and what the smallest scale is that we've dark matter on, so we can detect it on these huge scales. You mentioned that any modified theory of gravity doesn't work.
What is the smallest scales that we've detected dark matter on?
Yeah.
Okay, so as far as I know, the smallest scales that we've detected dark matter on are at galaxy scales. And even smaller scale, smaller than that is the smallest galaxies that we have are dwarf galaxies. And
Okay.
there's evidence to show that dwarf galaxies actually have more dark matter than baryonic matter. So they are very good test laboratory for dark matter. Yeah. But yeah, does that answer your question?
Yeah, sort of, and it was kind of a two-parter with the mass matter power spectrum. 'Cause I've heard the other ones before, but.
Can I get back to you on that one?
Yeah, absolutely.
Yeah.
Good, so we've got a question from online. So you said we're
Right.
moving in the wind through the dark matter. Why doesn't the dark matter halo, why is it not rotating the way we are?
So it's a question of relativity, right? So it's a matter of the fact that our galaxy is rotating. Our galaxy is rotating in a certain direction. And so the dark matter itself is just sitting in there in our frame. It's just sitting in there, but it's not co-rotating with us. It's just sitting there and having different velocity directions. And so the reason that we kind of think of dark matter coming towards us is that as I'm moving through this thing, the dark matter particle may have some small component velocity in that direction or that direction or that direction. But in fact, the big component is the fact that I'm actually moving, it's moving towards me or I'm moving towards it at that 220 kilometers per second.
Yeah,
I'm curious about the methods of detection, specifically the recoiling with electrons.
Yeah.
How is the dark matter interacting with the electrons that cause it to recoil? Because like, isn't the whole point that at that scale, the photon is what's causing the interactions between charged particles? So the whole point is that dark matter doesn't interact with photons?
So dark matter, no, it's not necessarily, it's not the photon. Okay, so what we have here is that I mentioned that I'm releasing a photon. So in atomic physics, so when I have a nucleus, I kick out an electron, that usually releases a photon.
Yeah.
Yeah. So the dark matter is actually interacting with the electron directly. So it's
How?
it's a direct interaction. Think of it as a billiard ball interaction. Now, I don't want to go into quantum mechanics because that's not really what happens. It's actually fields that I interact in. But think of it as a billiard ball. The dark matter just comes in and kicks out an electron, and a photon gets knocked out from it. And so I'm detecting this photon that comes out. That's this light that comes out from that.
There wasn't the slide with the two gas clouds combining, wasn't that saying that dark matter doesn't like directly interact with other masses?
It doesn't interact with itself,
Oh, okay, I'm sorry,
Yeah.
okay, yes.
not with itself, but there's some non-zero probability that it will interact with standard model particles.
Okay.
Yeah. And so this is why we set up this experiment. So if dark matter do not interact with us, so you could actually ask me the question, what if dark matter does not interact with us at all? Why are we doing this? Right? How do we detect dark matter if it does not interact with us at all? If this interaction is zero, then we would have to look at some sort of gravitational type interactions, which actually we are doing parallel to this search for dark matter.
Oh, thank you.
all right, we've got a question from online. If dark matter has energy, would it be possible to harness this energy?
I do not think that is possible. If we could detect this dark matter, then maybe it would be possible to harness the energy. But no, I don't think so. That simple answer is I don't think so. I don't know, but I don't think so.
All right, yeah,
there are a lot of observations which show the absence of dark matter, especially those are coming at higher redshift. For example, if you take the galaxy rotation curves of galaxies at higher Z likes high redshift from say 0.6 to 2.5 or something, there have been reports that they have their rotation curves are declining just like the Keplerian curves. So how do we explain the absence of dark matter in so many structures in the universe?
I have not actually come across those yeah. I do not have an answer for the question. I do not, yeah, I haven't come across those. I've heard of like 1 or 2 galaxies that apparently lack dark matter, but as far as I
There are
know,
hundreds of galaxies, thousands,
okay.
which don't have any dark matter.
Another question.
Sorry, we've got one from online and then from Doc. So you have your pie chart of the energy budget of the universe. So what does can you explain exactly what the pie chart means? What does the size of each slice represent?
Oh, okay. So this pie chart indicates the energy density of all these different sectors in our universe. So the baryonic matter only takes up about 5% of the energy density of our universe. The dark matter is only 26% of the energy density in our universe, and the dark energy is about the rest of about 70%. And I think about this as, so dark energy is what's responsible for our universe expanding, and the dark matter is what's responsible for everything sticking together. So think about if I took a balloon and I blow into this balloon and it keeps expanding. But as it expands, all the particles start congealing together as this thing is expanding. So the congealing is a function of the dark matter, and this expansion is because of the dark energy. And so you look at some other data that tells you that dark matter actually has 85%. It forms 85% of our universe. It's actually the 85% of the matter, total matter in our universe. But the energy density is in 27.
Doc?
Yeah, I just you had a picture that made me curious here, because I never thought of this. Like then you had this picture of the Milky Way, right?
Yeah.
This is spiral galaxy, it's plane. And then the plane of our solar system, are they aligned, or what angle are they? Do you know what angle they are on?
So this picture?
Yeah, I think maybe it was another one actually, but it was similar to.
Oh, this one.
Yeah, I think what's this one where we're kind of flying through. Are we kind of the plane of our solar system aligned with the Milky Way, or is it an angle?
No, it's not. So what do you mean? So this is the
Yeah, I
this
see.
is as we're moving in the sun. The plane of our
very cool.
rotation, and the solar system is just moving around the planet like that. And this is quite interesting. This is quite interesting because we can actually use this motion to detect, for different detections of dark matter. This is what we call annual modulation or daily modulation of our experiments. So if I have an annual modulation, I know that the sun the Earth is moving around the sun in a certain direction. And so there's certain times of the year where the sun is moving towards the dark matter. There's certain times of the year where it's moving away from the dark matter. And so we believe that dark matter is the only one thing that has this kind of property, or should be the only astrophysical object that has this kind of property. And we can kind of search for this kind of thing in our experiments. Yeah.
Other questions in the room?
For the neutrinos, at the beginning, I think you mentioned that we need some way to distinguish between other sources of neutrinos and dark matter neutrinos. And one way we can do that is to look at the direction that they're coming in from and ignore the ones that are coming in from the sun.
Yeah.
For the later method of looking at neutrinos caused by dark matter interactions from high energy particles from the sun, how does that work? Because those neutrinos, are they coming in from the direction of the sun, or are those also from all directions?
So let me maybe I didn't say it clearly. So in this here, we have neutrinos that are coming into an experiment. So I have an experiment that is meant for green particles. Now I have these red particles that are produced somewhere else that are actually coming in and producing the same signal. Now my detector is colorblind. It cannot determine which particles came in and detected. In the later thing where I have these neutrinos that are hitting the dark matter and causing them to interact, is the fact that neutrinos are actually very, very weakly or feebly interacting particles. And there's an idea here, or theoretically you can think of dark matter may interact much stronger than neutrinos. So I'm actually kind of sacrificing the interaction of neutrinos coming into my experiment with them actually giving a boost to the dark matter and the dark matter coming into the experiment. Now, if I see a higher rate of these particles coming into my experiment, I know it cannot be neutrinos because neutrinos have a certain interaction strength with the standard model that is much weaker than what that, and we kind of know, we can calculate that interaction.
Okay,
Yeah.
I think I understand.
Yeah.
Yeah, so I'm just thinking, so for example, if we were to detect dark matter in a collider, we would learn that, you know, a proton-proton collision could produce dark matter with a non-zero branching ratio. So in terms of direct, indirect, or collider positive dark matter detection signals, what would allow us to kind of infer the most about the nature of dark matter between those three?
Very good question. So one of the things that I didn't mention in this plot is the idea of complementarity. So by complementarity, what I mean with that is that if I see dark matter in one experiment, naturally I expect to see it in a different experiment. So as you say, the LHC or Collide experiment is this thing that's going to allow me to determine the inner properties of the particle. If I determine a dark matter from direct detection, right? I cannot tell you much about this particle except the fact that it has a certain energy and it must have a certain mass range. Is it a fermion? Is it a scalar? I have no idea. Now I have to look at the LHC. If I saw it in my direct detection experiment and I'm 100%, I can bet my house on, I don't have a house, but I could bet my house on that this is a dark matter particle, then I would have to go and look at a collider and I must see it at a collider. And then at a collider, then I will have to do some in-depth studies to understand what this particle is.
We've got a question online. Okay, yeah, I can't see it there, but yeah, okay. Is tired light or covariant coupling constants models dubbed CCC plus TL model, excluding the dark M and dark matter and dark energy as serious model to consider?
No, I do not know of those, and I have no idea. So any of these models that modify gravity or modify the nature of how we're doing things today, they have to explain how dark matter, how the data that we have basically. So I talked about rotation curves. You know, if you have a model that says I can explain the rotation curves, and then I go to a larger scale, can I explain the galaxy cluster scales? Okay, I can go consistently explain the galaxy cluster scales. If I go to even larger scales, can I explain that? If a model like that can explain that, but also is consistent with other observational constraints that we see, then that is a model that I can think about. But if a model is, and this is me personally, but if a model says I can explain this, but I can't explain that, but I can explain this, but I can't explain that, then there's some issues that I necessarily don't think about. So I'm not saying don't consider it, but I personally don't.
Great. Yeah.
What is your favorite dark matter candidates?
I'm actually surprised that lasted this long. Before someone asked me. My favorite dark matter candidate, I can say without surety, is the one that is.
Four. Yeah.
Can like a theory of quantum gravity maybe someday describe like the observations of dark matter energy?
Quantum gravity?
Yeah.
Maybe. I don't know what quantum gravity, so and I don't know what the current status of that is, but it could, maybe. Yeah.
All right. Well, thank you everyone for the wonderful questions. Thank you, Professor Mohlabeng again.
As I said before, I'm Jesse Heilman, the regional coordinator for this leg. Not done yet. Of the 2024 CAP Lecture Tour Series. At this time, I'd like to thank the national coordinator, Professor Gwen Grenier, and our staff at the CAP office, the university coordinator, and Professor Stolarski for helping organize today's talk. And thank you, Professor Mohlabeng, for an excellent presentation. Thank you all for participating. Thank you to the CAP Foundation and its generous donor who provided an endowment that has made CAP's Lecture Tour possible. Please consider making a charitable donation to the CAP Foundation today to support this and many other significant programs, such as supporting scholarships, prize exams, resource development, and other activities of physics students. The sixth and final talk will be by Professor Jason Holt on Tuesday, April 2nd at 11 a.m. Eastern, who will speak on neuromorphic hardware and its role in quantum technologies, and I hope you can all attend. As a reminder, all participating students, both online and in person, are invited to remain to have informal discussions with Professor Mohlabeng, and online participants may now unmute themselves and turn on their videos. Have a great day, and thank you.
It's at 5:30 Eastern.
5:30 Eastern? Oh, it's, yeah, sorry, the script says 11:30, but it says 5:30 Eastern on this. We will confirm this, and the information goes out from CAP. Hopefully they will have the right one, and it's on the CAP website, so I'm betting that this one is more correct, so probably 5:30 Eastern. Thank you, that's all.